Actually, uh, so before giving this talk, let me just give a little bit background that so I didn't get much time for preparation. So I just like crude way of like the slides, whatever I prepared. And many places I may have forgotten citing the original paper. So it is done in a hurry, but not intentionally to not giving reference, etc. But anyway, so and before when Professor Manoj approached to me, I really tell you that I had no idea about this program and the talks which was going on. Like few days back, I first went through the talks. Like I wanted to know like what is the background, how many talks are given, who all gave talk, and on what topics, because then it will be easy for me to plan the talk. And I'll tell you that I'm really happy to see so many nice talks. And like particularly after these so many talks, it's good for me that the audience is already aware of the basic states, the quantum states, and the various physical properties, and what is important, what not, and at least some introduction to the basic terminologies of this field. So particularly, I think the talks of the quantum materials by Professor Bahadur Singh and Shekhar was really nice. And then Subhajit also gave very nice introduction of quantum materials on thermoelectrics. Even Professor Ajit Patra and Surjit Singh from ISR Bhopal, they gave really nice talks. I liked their talks. And towards end, I saw that Professor Sunil Singh from CSR NPL gave a very nice introductory talk on the thin film deposition. So basically, this covers most of the major topics. So when going through, I realized that maybe it is good idea when I'm planning this talk, because see my I'll next few slides I'll first give you the little bit basic background of as a speaker of me, what I have done so far. But when I was preparing the talk, I realized that maybe it will be good idea if I do not focus on the the experimental results, or too many discussion on papers, particularly publications. But if I focus on the basics, maybe it will be a good idea, because as Professor Manoj also told me that most of the faculty members who are joining in this webinar, they are from different background, diverse background, not particularly working on quantum materials. And I am also experimental physicist. So for me, frankly speaking, big equations, and I'm not a theoretician, so those abstract equations I don't understand. So what I try to do is that I try to understand what, if a expression is there, what it represents, and what is the take-home message from there, and how to observe as an experimentalist, how to observe it experimentally, and how to control the outcome of this, so that we can observe those quantum states, we can control the quantum states, so that if certain material does not show those exotic behaviors, how to design the materials so that we can arrest those states in a real material. Okay, so this is my approach. So what I planned is that please stop me whenever like 1 hour is over, and because it's just one talk, I didn't prepare two different talk, just one talk. But from very basics I started, because I am teaching IIT Delhi a basic, like a course on introduction to quantum material to MTech students, MTech solid state material students. So already some slides taken from my class, and I like to like give you a very deep and very basic understanding without the equations as less as possible, so that at least there is some take home message, you can feel that okay, this is not waste of your time. So that is my main motto. So before going, I think most of you may not know me, so that's why I thought maybe first 2 or 3 slides I'll give some introductory so that at least you know me. So I have been working on this quantum material field from last I think almost 10 years, and uh, so and I have major contribution into a different field in this quantum material. First is this discovery of chiral topology. So these are all my papers, publications, and most of the recent one, it is appeared on 1st January in Nature. So here we covered on the discovery of chiral topology, how to like control it and all these experiments. So I'm very proud to tell that most of the major discoveries in this field are done on my own single crystals. So these are some single crystals which I had grown. And the second part is discovery of quantum magnet. So the magnetic wild semi-metal. So this is the first discovery, the first compound which was discovered. I am part of that team. So this is my single crystal on which this work was done. This is the 2019 this science paper, and then later there are many follow-up papers. So now after this I joined in IIT Delhi in 2020. So this is my small group of students in IIT Delhi. So this is my web page. Please visit. And in last 5 years, as I said, I am experimental, I'm working on experimental background. So we have developed various crystal growth facilities in our lab, starting from Bridgman to flux growth to two-zone furnaces, and then we have crystal orientation wire saw, Lave diffractometer. At least from crystal growth point of view, we are independent. And the basic characterizations that we do, it is in our like department shared MPMS and PPMS facilities. And so as I said, our group is very new. So publications also started coming off. So just 5 days back, this PRB was accepted and I put it online. And there is another paper which I think this is the first publicly I'm telling about this work. So we are very proud of this. This is in the review. This is entirely done in my Indian like IIT Delhi lab. This is under review in Nature Materials. And just to briefly tell that if you know the magnetism, basic magnetism, let's say the exchange bias. Exchange bias means there is the magnetic hysteresis loop, and by cooling, by control cooling, you can shift the exchange bias, this hysteresis, to a magnetic field direction, and amount of magnetic field, how much it like shift, it is called the exchange bias field. And so far, if you look into literature, most of the compounds, the exchange bias it shows is almost in the range of like few hundred Oersted. And Tesla to Oersted means 1 Tesla is 10 to the power 4 Oersted, so 10,000 Oersted. And most of the compounds, it is the coercive field is very high. So if you want to have a practical application, ideal is that the coercive field should be very low so that antiferromagnetic spintronics you can do, and the exchange bias field should be very high. And we have found that the best 2D material in ever reported is Fe one third. These stars are actually 2D materials. So this is intercalated compound, so it's very difficult to control the composition. And the 3D material highest is around 2 point, like 3 Tesla, 3.3 Tesla. But in our compound, whatever we have discovered in IIT Delhi, so this is a 2D material. For the first time, we have shown that there is no training effect at all. It doesn't matter how many times you switch the magnetic field. If you have 1 Tesla exchange bias, it is locked 1 Tesla exchange bias. Even cooling field also 300 Oersted, very low, but you can get exchange bias up to beyond 7 Tesla. 300 Oersted is nothing because the play magnet, usually the kids play magnet, it can be up to 1000 Oersted, so it is nothing. So we have got the ideal magnet that one can dream of. But anyway, so this is compounds are like these papers are going on. But in this talk, I am not going to cover any of the research work that we have been doing right now. So I thought I'll discuss the basics of quantum material. What is the quantum material? And I'll take you from discovery, and then one by one constraints will try to move so that we hit the material. Like you understand, like how these topological states arrive, what are the properties that save or let's say protects these topological states, what happens if you break those states, how to manipulate them, and then finally the experimentally how we observe, because most of these quantum material states are they are in the momentum space. So far the talks which I have gone through, there are, let me tell you that there are two different class of materials. One is the real space effect, which in India. So there are like last few decades, people are working on magnetic materials, where we have the ferromagnetic, antiferromagnetic, different kind of magnetic materials, where we have the spins, we play with the spins, we can have skyrmions also with that. So everything is in the real space. But if you think that that is quantum material, I'll say that it is very wrong. It's a different thing. Because quantum material, it doesn't mean that a material has quantum mechanics means it's a quantum material. No, it is not. Because every material you take, there is hidden quantum mechanics. But in the macroscopic level, that quantum property is getting dominated or not, that is the matter. Because in that sense, the magnetism, whatever we have been investigating over decades of India, it's not actually the quantum material, because this quantum material boost, it came just 10 years or maybe 15 years back. So what is the new thing, why people are so fascinated about this new topological states, or let's say the quantum material, that I'm going to discuss in this talk, and I hope I'll be able to explain you with basic terms what makes these compounds different than the compounds which we knew so far, the classical, or let's say the real space quantum materials, or let's say the real space spin textures, where we have the spin dependent, or let's say spin controlled systems. And the compounds which I will be talking, it's actually in the momentum space. The properties is we are controlling is in the momentum space. So the first topological material that was discovered, it was in 1980s. So that is the quantum Hall effect, and because of which Professor Klaus got a Nobel Prize in 1985. So if you take a 2D electron gas, a 2D electron gas can be at the interface of LaOH2, or you can have this gallium arsenide or aluminum doped gallium arsenide, or any of these devices where you can have 2D electron gas at the interface of this device. There, if you apply the magnetic field, then you can observe that there is a certain field, like the in the Hall response, it is shows like a plateau as well as the jump. And wherever you have the plateau, you have perfectly zero resistance. The magneto resistance, not, I'll say that the resistance, rho x, the longitudinal resistance, it goes to zero. And at the same time, the Hall signal gives a plateau, like it's a quantized signal. For the long time, it was a debate, or let's say the it was a like people are struggling to understand what is the origin of this. So let me take you through the process, what is the origin behind that. So if we apply magnetic field, and I know that many of the previous talks they have covered this, so I thought maybe it will be a little bit refreshing for many of you who might know. So it is maybe good just a refreshing part. Okay. Anyway, so when we apply, let's consider that you are applying magnetic field along the z direction. So if you have a system like that, where this is a 2D electron gas, please try to understand that this 2D electron gas means this is actually a gapped system we are talking about. It's not a metal, but it is having a finite gas. You can think of an insulator or semiconductor, whatever it is. At the end, it's a gap system. It's it's a semiconductor or insulator. Now, when you apply the magnetic field, then in presence of magnetic field, the energy of the system, it is not having continuous, but it has the quantized states like this, the n plus half h cross omega, where n is the considered the Landau levels, because now the energies are split in different energy levels. So this was the continuous spectra without applying magnetic field, the dispersion relation. Now, when we apply the magnetic field, the electrons are distributed in quantized level, and these levels are called the Landau levels. And the difference between the energy difference between two Landau levels is half h cross omega. As you can see, this multiplication of half h cross omega. See, what is omega c? This is the cyclotron frequency. This is function of magnetic field. So if you increase the magnetic field, the strength of the magnetic field, this is what is in our hand. We can increase the magnetic field to whatever value we want. This is the external perturbation applied. So with the increase of the magnetic field, as you can see, this energy is a function of magnetic field. So obviously the separation between this Landau level increases. So Fermi energy is already fixed. Now as you increase the magnetic field higher and higher, let's say you go from B1 to B2 to B3, as you go to higher and higher field, number of Landau levels, it increases and goes beyond the Fermi energy. Now, there is a catch here. Let's say you have 1,000 number of electrons, total 1,000 number of electrons. Earlier, it was distributed in, let's say, 5 number of Landau levels. So now with increasing magnetic field, already one Landau level gone out from the system from Fermi energy. Then what will happen to those remaining the electrons, because it cannot escape beyond the Fermi energy, because Fermi energy is decided to the energy where the last field state is present. And these are electrons are fermions. That means it follows the Pauli exclusion principle. So if the states below Fermi energy is already filled, then when one Landau level goes up, crosses the Fermi energy, then how it is possible that already the field state is accommodating more electron? So the reason behind is the degeneracy of the Landau level. Like like the energy difference is a function of magnetic field, the degeneracy of the Landau level is also function of magnetic field. So if you make a calculation, then you will find the degeneracy is B by phi naught. What is phi naught? This is flux quantity. This is basically universal constant H by E. So this is directly, degeneracy is directly proportional with respect to magnetic field. Higher the magnetic field, higher is the degeneracy. So it doesn't matter how many number of electrons you have. The moment you apply the magnetic field stronger and stronger, the more number of Landau levels crosses the Fermi energy. So the remaining Landau levels, degeneracy increases. It can accommodate extra number of electrons. That is how even we can go to last Landau level, where all those 1,000 number of electrons we started with, it can be accommodated in one Landau level itself. So the last Landau level is actually the highest magnetic field, whatever plateau we get. But I will discuss about this, how to experimentally find out whether we are sitting at the last Landau level or the second last or third last, who controls that value, and how we can experimentally determine that. So this is the picture. Once again, I am showing that we are applying the magnetic field and we have the plateau, the Hall plateau. And if we compare with the dispersion like this, energy dispersion, then what we see is that wherever there is a jump, it is not a delta function, but there is a certain slope. From where this slope comes? Slope comes because it doesn't matter how perfect system you prepare. There is always some defect induced scattering, it will be there, because of which there is a broadening of this Landau level. So whenever this Landau, the Fermi energy hits to one Landau level, there is a broadening. So you get this jump in the resistance, the Hall resistance, as well as the longitudinal resistivity. It shows a finite value. It's not zero, but a finite value. Because now you have the certain density of states, so it's a metal. It behaves like a metal. However, once a Landau level goes, it crosses Fermi energy when it is perfectly in the gapped state, like in between two Landau level. Ideally, system should be insulated. But when we do experiment, we see that there is zero resistance. So this is very opposite behavior, whatever we see. A insulator behaves like a perfect conductor. How it is possible? So if we want to understand that, then we have to look into its the detail electrons. What is the response of these electrons to the external magnetic field? Is that, see, this is a gapped state. As I said, this is a 2D electron gas. So we have insulator or semiconductor. Now the moment you apply the magnetic field, what the electrons does is that it gives a Larmor precession. So Larmor precession, the cyclotron frequency, that is what we are observing here, omega c, cyclotron frequency. And the electrons which are sitting at the edge, as you can see, it cannot fulfill its full precision. So basically it follows. So if this is like let's say left-handed circularly like rotation, then you can see here it hops, like it's going down, then here, then here. So if there is an electron which is sitting at the edge, it has no other choice but to move forward spontaneously. in presence of the magnetic field. So it goes in the, let's say, left hand side. Then when it reaches to other side, it is the other circle which is in the right hand side, which was cut. So obviously in this side, the bottom side, it goes left hand side, other one is right hand side. So this is the chiral motion or the chiral edge state. That is how it is coming. Chiral edge state, helical edge state, same thing. Different terminologies, different papers, it represents the same thing. Now, when we do the experiment, real experiment, we can calculate the resistivity. From there we can calculate the conductivity, and if we plot it in this form like E square by h, then what we find is that this plateau, it is an integer number of E square by h. What is this integer represent? So this integer is the topological invariant of this system, because as I said, this is the first quantum number. Why it is the quantum material? Because in an insulator we are observing the trivial, or let's say in an insulator we are observing a topological edge state or a zero resistance state which cannot be explained with classical way. Okay, so this C, this is the invariance number, or this is the integer. What it actually represents? This represents the number of Landau level up to that Fermi energy. If Fermi energy is here, let's say number of Landau level is 2, you get 2 into E square by h. You increase the magnetic field. If it goes like this, bottom here, if one number of Landau levels, then C equal to 1 E square by h. If you convert this into conductivity, you will observe only E square by h, 1 into E square by h. 1 means you are observing, you are in a state of last Landau level. So in this topological phase, the Chern number or the topological invariant represents the number of Landau level up to that particular Fermi energy. Now, when it is C is not equal to 1, because here as you see that I have shown C equal to 1, number of edge state is 1. Now, how to understand mathematically? Let's say if C is not equal to 1, let's say 2 number of Landau levels, 3 number of Landau levels. See, 3 number of Landau, see at this Fermi energy, there are already 2 number of Landau levels. How it is possible that 2 number of Landau levels gives 2 edge state? How it is possible? In this picture, you cannot understand that edge state, because you see Fermi energy is here, Landau levels are already below. Then until unless the Fermi energy crosses the Landau level, it cannot contribute anything to that Fermi energy. So for that, we have to go to another picture which says that bending of the Landau level. So this is the full picture, what is showing, whatever I showed earlier, this is actually within the material what is happening. But when you go from out material, inside material to outside material, there is a crossover, which is the edge of the material. Beyond the edge of the material, the potential is infinite. So the electrons which are already inside the material, until unless you overcome that edge, the barrier, the infinite potential, or let's say the work function, you cannot take out that carrier outside the material. As a consequence, what happens is that if you plot the dispersion here with respect to energy, then you see that the Landau level which is inside the material, it is flat. As it goes towards the edge, the Landau, because the outside potential is infinite, these levels has to bend. Since the bending of this edge state, when you cross the Fermi energy, you see here at the edge, the Landau level cross the Fermi energy. As a consequence, if you have 3 Landau levels inside the Fermi energy, you have 3 edge states, because now 3 Landau levels are crossing this Fermi energy at the edge of the material. So you get C equal to 3 in this case. So this is how in this quantum material, the invariant, the topological invariant represents 3 edge states, which is nothing but number of Landau levels. In this case, 3 number of Landau levels present until that Fermi energy. Who controls that position? The number, it is the magnetic field, applied magnetic field, which is in our hand. Okay, next. Now we are slowly moving from quantum Hall insulator. Whatever we have discussed is the quantum Hall state. This is a insulator we discussed. It's a gap state, gapped material. So we are in a quantum Hall insulator. Now we'll move from this picture to a topological insulator picture. We'll see that first what all ingredients are present in this state. Then if you want to have a topological insulator, we do not apply any magnetic field. We do not need to apply any magnetic field. Still, how you can arrange the same topological state, same edge states what we are discussing. So the quantum Hall insulator, there are three important points here is that the two-dimensional electron gas you need to have, and it is observed that this state is at very low temperature, and in order to observe such behavior you need to apply very strong or very large magnetic field, which are the problem for, let's say, practical applications, and we want to get rid of them so that we can design a material with our easy conventional route, or let's say easy manipulation. So first, what we'll do is that we'll remove the magnetic field. We do not need to apply magnetic field, because the applying strong magnetic field few hundred Tesla is beyond the any practical application, let's say device you want to apply. You cannot carry a 10 Tesla magnet to a device for a practical application. This is the first thing what we'll try to get rid of. Now, what happens if you how what are the different ways that you can remove the external magnetic field? The immediate solution is that let's use the internal magnetic field. Internal magnetic field is also possibility. Let's say you go from a non-magnetic material to the electron gas, it's a non-magnetic material. Here we break the time reversal symmetry by applying the magnetic field. We can have the magnetic material where we have the internal magnetic field because of this magnetization, the exchange interaction of the spin-spin exchange interaction, or let's say the ferromagnetic materials, it gives the internal magnetic field. Let's use that internal magnetic field to replace this external magnetic field. If you go to internal magnetic field, then what is the picture we arrive is quantum anomalous Hall effect. What is the difference between quantum Hall and quantum anomalous Hall? So I just made this table. As you can see, external magnetic field quantum Hall state is required, quantum anomalous is not required. In quantum Hall effect, what is the topological invariant we was discussing? That is the number of Landau levels. In quantum anomalous Hall effect, there is no Landau levels because we have not applied magnetic field. So there is no chance of this magnet this whatever we have shown here, that the energy states are continuous, right? Until unless we apply the magnetic field, the Landau levels will not appear. So if you do not apply magnetic fields, no formation of Landau levels. That is the clear part. So for the anomalous Hall effect, you do not need to apply any magnetic field. You are using the internal magnetic field. So there is no consequence of forming the Landau levels. The origin of topology, the quantum Hall effect, is the magnetic field, what we have applied externally. But in quantum anomalous Hall effect, it is the band structure. And in the first case, the time reversal symmetry is broken by the magnetic field. The second case, it is the internal magnetization. The Hall conductivity, the result of this, what we actually want is that the edge state, the continuous, the dissipation like edge state, whatever it was there on the Hall insulator, can you have the same? Answer is yes. In quantum anomalous Hall effect also, irrespective of all these things, we get quantized edge state. Now, what all ingredients for this? What is the things which you have to keep in mind so that we can arrest this? First thing, what you have to understand is that this magnetization, whatever I said, this is perpendicular magnetization. If the moment the ferromagnetic material forms domains, it is gone. So if you want to have a quantum anomalous Hall effect, you must have perpendicular magnetization, single domain magnetic structure. Otherwise, there is no possibility of arresting quantum anomalous Hall effect. Second thing is that time reversal symmetry is broken. So that you have the edge state. By the anyway, the time reversal symmetry, I have detailed slide, 2-3 slides I have where I will be discussing the edge state, the time reversal, the time reversal symmetry, what it is and what it represents. I have the slide, so I'll go into that discussion. But the same picture, the schematic picture, whatever I showed in the Hall insulator, if you look at the comparison with respect to quantum anomalous Hall, in the quantum anomalous Hall, again there is the difference. Outside is the vacuum, the trivial insulator. Inside is the non-trivial material, where you need to have strong SOC. Again, in the next slides, I'll be discussing each of these points. What is the role of SOC? What is the Berry curvature? How it comes? How it controls this edge states? Everything I'm going to discuss a lot. But what the neat result is that at the boundary between this topological non-trivial and topological trivial state, you get this spontaneous edge state, the metallic edge states. Next, we are going from quantum anomalous Hall state, or let's say quantum Hall insulator state, to topological insulator. What all ingredients you need? What are the must tick conditions so that you can arrest the topological insulator state? First thing is that, of course, the bulk has to be insulated. That is the starting from the starting point everywhere, whether it's a quantum Hall insulator or quantum anomalous Hall, the bulk must be gapped. If bulk is metallic, there is no possibility of edge state. So bulk has to be gapped. Second thing is that now we need, yes, Charn insulator also. And this I'll be discussing again, the Charn insulator. I'll be coming into that. So the strong, we need strong spin orbit coupling. What is the role of spin in orbit coupling? That will also I'll be discussing. Then we need the band inversion, time reversal symmetry, and then the non-trivial topological invariant. The topological invariant in this case, the topological insulator, is called Z2 insulator. What is Z2? That will also I will discuss. So let me go one by one, all these things, what every step represents. First is SOC. What SOC does? SOC means spin orbit coupling. Immediately it will add one term in the Hamiltonian, lambda L dot S. Okay. What is this lambda? Lambda represents the strength. What is the consequence of this? Consequence is that it moves some bands up, some bands down. As a consequence, you can have band inversion. Okay. Another point of SOC is that earlier case, as I said, that we need to have a situation where we don't need to apply magnetic field. How can replace magnetic field? Magnetic field means the internal magnetic field we can use is SOC also. Let's say SOC means what? The spin orbit coupling. What happens if you have heavy materials? Let's say Z is very high. So in case of Z very high, in the rest mass of the electron, what you see is that the nucleus, which is large, see, heavy nucleus means large number of Z. So in the rest mass of electron, which is red particle, you see that a large mass of charge carrier which is moving around. It's like sitting on the earth and seeing the sun roaming around. So what is the consequence is that a moving charge particle induces magnetic field. This is the magnetic field what we are using, the internal magnetic field coming up from the strong spin orbit coupling. And as you can see, this is proportional to Z to the power 4. That is why for the topological compounds, whatever we want band inversion or whatever, we prefer to have heavy materials like bismuth, selenium, telluride, like these compounds, where you have large Z. So in this material, when you have band inversion, let's say the popular semiconducting material, the conduction band is always made with, let's say most of the, not always, I should not say always, most of the popular compounds, the conduction band is made with S band, S orbital, whereas the valence band is made with P orbital. Now you have the hybridization of that. When you have the hybridization, now spin orbit coupling, under spin orbit coupling, spin and orbital are no longer independent of each other. So we have to invoke J. J means L plus S to L minus S. The moment L plus S to L minus S form, the Hamiltonian, which is 2 by 2, if you solve the Hamiltonian, the energy you get is E naught plus minus V. What is the V term? V term is the consequence of this LS term. That means the net energy after SOC, after incorporating the SOC, it gives energy plus V, energy minus V. That means after the band inversion, once you incorporate SOC, once you have the hybridization, then the bulk automatically gaps out. So in the bulk, you satisfy the condition that the bulk must be gapped. So with the SOC, with the band inversion, now you have achieved the state that bulk is gapped out. Okay. What is the next consequence? As you can see, there is a part we have, because of the band inversion, part of the conduction band is gone to the valence band, whereas the valence band, part of the valence band has gone into the conduction band. As a consequence, you give rise to Z2 invariance. What is Z2? So I'm going, by the way, I'm going step by step. First is the bulk gap SOC. Time reversal symmetry, I'll go next, but first let me go introduce the topological invariant, what it is. Then we'll come to time reversal symmetry. So what is the topological invariant? In this case, this is called Z2. Everywhere, whatever research paper you read, always people say that, oh, topological insulator, whether Z2 invariance is protected or not. What this Z represents? What Z represents is that this is actually came from the German word Zahlen. What it represents is the number, the integer number. So Z represents the integer numbers. Now you can connect this Z with the topological invariant that I have introduced in the quantum Hall effect. Like there also we have the char number C, which is the integer. In this case also same integer but different name. In this case Z is from this Zahlen, and it represents Z2, it's actually from the group theory. When we say Z2, then obviously there are some elements present in this group. What are the elements for topological materials? For topological insulator, it can have only 0 and 1 state. Nothing else is possible. If it is more than 0 and 1, that means this topological state, whatever we are dealing with theoretically, this is not topological insulator. This is some other topological state, not topological insulator. So what 0 represents in this Z2, 0 represents the trivial state. That means bulk is already gapped because of the SOC. As in the previous slide, I have shown that bulk is gapped. That means Z2 equal to 0 is satisfied. Z2 equal to 1 means non-trivial state, the edge state. What is the edge state? Edge state is the gapless state at the edge of the material. And how it appears? Okay, sorry. In the next slide, I'll show. Okay, how the edge state appears because of the band inversion. Everything is connected. Okay, with that. So here I have explained you the Z2 invariance, what it represents, what the number represents, and the in if you have the quantum Hall state, the integer the Z, this is also same of C, that the topological invariant or the char number. You can have 0, 1, 2, 3, 4, 5, 6, any number. What it represents is number of Landau levels. So you can have any number of Landau levels. So this is for the quantum Hall effect. Whereas for topological insulator, either band is gapped, bulk is gapped, which is 0, or you have the edge state, or not only or, and you have the edge state, which is Z2 equal to 1. That means the topological edge state. So this is the Z2 invariance. Next, so these are the three parts which I have already explained: SOC, band inversion, G2 topological invariance. Now I am coming to time reversal symmetry. What time reversal symmetry does is that it operates on the time t, and under time reversal symmetry t goes to minus t. As a consequence, in the momentum space, k goes to minus k. So what together represent, if you want to see the picture from a broad sense, if you have a state with plus k and up spin, then after applying the time reversal symmetry, the same state will become minus k and down spin. But you cannot have in between state, that means intermixed state. That means you cannot have plus k with down spin or minus k with up spin. If you want to have minus k, then it will be down spin. If you want to have plus k, it is always up spin, because it is called time reversal symmetry. And this, the consequence is called the Cramer's degeneracy. What Cramer's theorem says that under time reversal symmetry, if you have a state k up, k and up spin, then the degenerate partner is minus k and down. So this is the energy degenerate state, equal energy state. So consequence of this is that spin momentum is locked. So if one spin is moving in the momentum space along plus k direction, and let's say it encounters a scattering cross section, then you cannot have that with the upspin it goes back direction. That is not allowed, because now what will happen is that the moment, because of the scattering, the moment the k becomes minus k, the spin also goes to minus the bottom spin, the down spin. So spin and momentum is locked. This is the consequence of the Cramer's degeneracy. Now, which are the high symmetric points, or let's say where we should be able to observe such Cramer's degeneracy in the material? Result is that in the Brillouin zone, depending on the crystal symmetry, different compounds have different symmetry in Brillouin zone. Some are cubic, some hexagonal, some can be completely different arbitrary shape. But whatever is the Brillouin zone, always in the Brillouin zone, which is in the momentum space, you have the blue color, whatever I have written here. So these are the high symmetric points which are time reversal invariant momenta. At this point, k equal to minus k condition automatically satisfied. So that means at this high symmetric point, if you have a band crossing, that band crossing is protected by the time reversal symmetry of the compound. So here is the importance of the time reversal symmetry. Now, if you put together the Z2 topology, then protected surface state, what it gives rise is that of the spin momentum locking is that the 2D topological insulator, the edge state is always you have one spin channel because of the up spin, another spin channel because of the time spin. So that if you want to observe the time reversal symmetry protection, there is no magnetic field. The magnetic field is replaced by internal magnetic field, which has already played its role by introducing the band inversion. And now, because of the consequence of that, we have got Z2 topology and time reversal momentum. So if there is a scattering cross section, let's say the up spin going forward and it encounters a scattering because of defect, because of some doping, because of the dislocation, whatever reason, it doesn't matter. If it is getting scattered, it cannot go inside the material because inside the material is already gapped out. It is insulated. So if there is a scattering, it has to remain in the surface only. Let's say what is the way out is that it can go either in the back way, in the forward. If it goes into the back way by after scattering, it adds the current to the down channel only. Or if you start with a down channel, then after scattering, it will contribute to the up channel only. You cannot have, because of the spin momentum locking, you cannot have any other possibilities. As a consequence, these edge states are by default protected by this terminology. So I have already discussed this and time reversal symmetry. Yes. Now you see how the Z2 invariance induces a surface state. See, in the bulk band, you already have the band inversion, whereas outside the material, it is, let's say, vacuum or air, anything. This is an insulator, trivial insulator. So if you connect, let's say, excitation from conduction band to conduction band or valence band to valence band. See here, because of the band inversion, part of the conduction band has gone into valence band, whereas part of the valence band has gone into the conduction band. So when you connect it, you see that there must be a point where these two parts cross section each other. That crossing is actually the surface of the material, where irrespective of outside is gapped, inside is gapped. At the edge of your material, you have a crossing point, which is the edge state of your material. And because of this time reversal symmetry protection, because it's not broken, you must have two channels, one because of the downspin, another because of the upspin. So this is the schematic diagram, how it is presented. The bulk is already gapped out, and you have the surface state, which is the spin polarized surface state. This is how it is showing. And this is the first prediction was done in 2006 only, just 20 years back. And then experimental verification was done just 1 year after that, 2007 itself. So this is 2D topological insulator. Now from 2D topological insulator, we are going to 3D topological insulator. So what is the 3D topological insulator? You can imagine a situation where, let's say, you have a metallic empty box. Empty box means inside is already air, which is gapped, already trivial insulator, whereas the surface is a metal, so the surface state. So this is the picture of a 3D topological insulator. You can construct the same by having 2D topological insulator and stack with each other also, so that you can make it 3D, like stacking of 2D topological insulator. It can give 3D, but the topological class will not be the same. The reason is that If you stack the 2D topological insulators, what happens? Not all the surface will have the surface states. Like as I said, in the 3D topological insulator, all the surface have the surface states. But if you stack, then top and bottom, which is already part of that insulator, you cannot have any surface state. So the surface state is already only in the edge. So this is how the two classification of topological insulator starts. One is 2D topological insulator, 3D topological insulator. From there it comes strong TI and weak TI. Weak TI means it is one of the example where it is stacked 2D systems. You can have weak topological insulator because of the scattering, etc. It is always possible that it will annihilate with each other. So this the in between the because of the stacking, the surface state may cancel each other. It can get merged with each other. Whereas if you have sorry, whereas if you have the 3D topological insulator, there is always odd number of band crossing, because of which even the surface states annihilate with each other. You will always have one, at least one crossing point which will remain. So this is called the odd, that is why odd number of Dirac cones will be there for topological insulator, strong topological insulator like 3D topological insulator. Whereas for 2D topological insulator, you have even number of Dirac cones, even multiplication of the Dirac cones. So these are some examples also of the strong topological insulator, weak topological insulator. So strong topological insulator, as I said, like bismuth, tellurium, and so sorry, this is typing mistake. Sb2T, T is in the small. So this is Te, tellurium, Sb2Te3, and mercury telluride. Uh, Confirming the age state. Okay, see, for the age state, you have to do the experiment. Okay, I think I have covered something in the age. I'll go in the next. There are two different ways how you can identify experimentally the age state. One is the electrical transport measurement. Second thing is that you can do the uh, uh, see, actually, this is all transport measurement, whatever it is there from the device. Okay, this is how they have experimentally identified the transport, like spin hall effect kind of experiment you can do, and you will get the edge states. You can get the signal of the edge state. Now the next part is that the 3D topological insulator, whatever we are talking about, how is the dispersion of the surface state? Whatever surface state we are discussing, I didn't go into that. So now I want to go that the surface state, the quasi-particle excitation of the electrons on the metals, like on the edge state. For that, what we do is that we make a comparison. If you see that, make a comparison with the relativistic particle and the topological insulator, you can see that the relativistic Dirac equation, if it is there, this is the typical Dirac equation which is predicted in high energy physics. The relativistic particles follows. You can convert that equation to a real material where the electron, as you know, the wave particle duality. So P you can convert into H cross K, and C can convert to nu. Nu is basically the group velocity, because now C is means the speed of light. Speed of light means in vacuum or in outside. But now we are discussing the carriers inside a material. You cannot expect that a material is moving with speed of light inside material. So what it does is that inside the material, when the particle, the charge carriers move, it moves with a group velocity. So we have to replace C with the nu in the high energy physics, this expression, and you get result is this term, this expression. So as you see that this is also experimentally, by the way, experimentally proved that the quasi-particle excitation of the charge carriers on the surface state of topological insulator, it behaves the like a Dirac equation, which is high energy physics. Now you must have, if you go through the literature, you will find that, oh, this is linear band crossing, this is massless Dirac fermions. Now let me just explain you why such exotic property comes, or what is the origin of such exotic property. Why we say it is linear band crossing. Linear band crossing means if you have the expression like this, then because of See, the what is M? M is called the mass term. This is a component of magnetic component. Okay. But in topological insulator, there is no magnetism. Okay. The time reversal symmetry is already conserved. There is no magnetism. So there is no mass term in the topological insulator. So if mass term is zero, in that case, the energy looks like this: E plus minus nu into K. So plus minus K means it's a linear dispersion. If you plot E versus K, it's a linear band crossing. Now, what is the consequence of linear band crossing? If you have a that is why, since the equation looks like a Dirac, which is followed in the relativistic particle, these charge carriers behave like a Dirac fermions because it's the uh, is the slide visible?
Yes, it is visible, sir.
Okay, okay, okay. Thank you. So in between it was unsaid.
Yes.
Okay. So um, so now you see the importance here that the surface, the carriers on the surface, because everywhere it is electrons only, whether we are telling massless fermions or Dirac or later we'll go while axions, whatever we tell, everywhere it is the same particle. Even holes does not exist. Hole means it's the empty state of electron. It is not a real particles, right? So everywhere it is electrons. So the electrons, but when we say it's massless, it is not the rest mass. It is basically the quantum mechanical entity. The curvature is not present of the bands. So there is no effective mass. So a massless particle moving on the surface of a topological material. Massless particle means it can move with a ultra high speed you can think of. So edge state, very less resistance, and consequence is the band crossing. Next, anyway, I'll go into that. What is more consequence of this zero effective mass? Like what is, so these are the experimental verification, by the way, that this the quasi-particle excitation, the surface state looks like a Dirac cone. So this is from Zahid Hassan's group in 2009. They have published this work, and this is the schematic diagram how this looks like the Dirac cone because of the spin momentum coupling, because of the locking of the spin momentum. It looks like if this is like anti-clockwise, the opposite one has to be clockwise. Okay. So okay. So please let me know when to stop and I can resume after that. Okay.
Okay. If you want, we can have a break of 5 minutes and then maybe we can continue again.
Okay. So is there any questions I can
Yes. In
answer?
the chat
Maybe.
box, probably you can see in the chat box there are a few questions.
Let me just uh, how to get out from here. Okay, now I get out here. Teams. How to open? Okay, chat. Hmm. Mm. Uh, this already explained. 3D top. Why zero effect? Why zero effective mass? Okay. See, zero effective mass you can think of here like the band is energy is proportional to K, just linear proportional to K. If you take dE by dK, first derivative, then it's a constant, right? The group velocity. The second derivative does not exist at all. If second derivative does not exist, effective mass also does not exist. It's a zero effective mass. This is, you can think of how the zero effective mass comes. Because I cannot say it is d2e by dk square equal to 0, because there is a danger into that. See, effective mass is proportional to 1 by d2e by dk square. So if you say 0, then it will be infinity, right? Which does not exist, then how you can take infinity? Uh, any other?
Yeah, till now there are no more questions, so maybe we can break for. Okay, your
Okay.
comments on symmetry protection.
Can you share your comments? Symmetry protection. Okay. Symmetry protection I didn't discuss much, but anyway, next, when I will go next slides, I will be discussing the symmetry. You see here, I think, yeah, Dirac. When I will come to Dirac, I will discuss in detail about the symmetry protection, how the symmetry introduces the protection, band protection, like inversion symmetry and the parity effect, how it is introduces. I didn't kill because see the symmetry, uh, the crystalline symmetry, okay, I didn't discuss much detail about. See, crystal symmetry plays a major role in this case because see who controls this time reversal invariant appointments. This is the crystal symmetry only. Let's say if you have a cubic space group or a hexagonal space group, your time reversal invariant moment of positions will change, right? So symmetry plays the role. So if you take a, let's say, cubic compound, you can make a switch out of it, topological switch also. Let's say you make a cubic topological insulator. I'm just giving a hypothetical scenario. Let's say it's a cubic topological insulator. Cut it in a rod shape. Now you apply uniaxial stress or strain. Either you pull out or compress it. What you are doing with that is that you are playing with the crystal symmetry. So it is possible that beyond after compression or like uniaxial, even not uniaxial, even high pressure also it is the same way. Like you take a material, apply very high gigapascal pressure also, you can change little bit the crystal symmetry. If symmetry is gone, then your the topological protection will also be changed, right? If earlier, let's say there was one, like say cubic, Brillouin zone, and there was one band crossing at the point R, okay, and now by symmetry manipulation, you have gone to a symmetry where at the R point it is no longer that it is not the same position, but you have changed the symmetry in such a way that there is no symmetry, crystal symmetry at R point. Then if there was a band crossing at R, there is nothing to protect, it will simply gap out. So from topological state to non-topological state you will go. So this is how the symmetry controls the topological states. Yes, I think there was another
There is one more.
chat. What it is chat. In the table which mass is referred to m, and if it is effective mass, no, sorry, uh, it is my mistake. I spoke it verbally, but I didn't write it. Uh, where it is? Let me go into this mass term. Where is the mass? Where I introduced mass? No, not this. Here. See, m is not mass. This is like a mass in the equation, but this is not a mass. This is the component of magnetization. The expression, I think I wrote it somewhere. Let me look at, because I should not tell the wrong actual expression. It is function of m z. Where is mass term? Z. I'll tell you. Just hold on a minute. Uh, where is the mass term? I'm very much forgetful about the equations. I don't remember equations at
It
all.
does happen.
So just 1 second. I have it now here. Yeah, M, mass. What is ah M equal to, let me write it here. What is the M equal to, it is small m, not capital M. And again, there's M equal to G. This is mu G equal to 2 for mhm, sorry, G mu P into mz. mz. Yeah. G and mu be universal constant. Mz is the Z component. If you apply magnetic field along Z, then Z component of magnetization. That's why I said, na, topological insulator, there is no magnetism involved. We are not applying any magnetic field. So mass term is zero. So this is the mass term. So no magnetic moment, no time reversal symmetry is protected. So M is zero in this case. The moment you gap out, you break the time reversal symmetry. This is the mass term because of which all the game is changed. Okay. So anything else?
No, I think now there are no more questions. So we can break now for
Okay.
maybe 4 or 5 minutes, and then you can
Okay.
continue again.
Okay. Okay.
Okay, thank you.
I think with intro itself, 2 hours will be gone. Anyway, yes, fine. So wherever time ends, just tell me that is enough. So I think I thought maybe because like instead of giving a conference kind of talk, maybe this might be more useful.
Yes, this is much more useful actually.
Because see, it is not possible in 2 minutes in one slide, one entire paper can be presented. It's not possible.
Absolutely,
So if
absolutely,
I
absolutely.
just flash, keep on flashing, then it's a waste of time.
Yes, there's no use. Yeah,
No
the
use.
people are faculty here, so they need these things,
Uh,
basic things.
yeah. So anyway, references are there. You can just give it like Google is there. You can just give it a slide, like give a search, and you get the original paper. And at least if the basics are clear, then those it's easy to understand any of these papers.
Absolutely. How's the weather in Delhi then now?
Ah, let me see. Oh, I think it's about to rain.
Same here in Jaipur
Now,
also it is the same almost.
now it's good weather. I'll say not too hot, not too cold. Cold is not
Yeah.
expected, but not too dusty. That is one. If
Uh,
little bit rain there every week, then it will be less dusty.
yes, yes, yes. The same in Jaipur also it's more or less same only.
Acha, acha. Jaipur, it's much better, right? Delhi is
Uh,
like
yeah,
four, five.
comparatively I think it's better.
See, 4 5 days no rain means there will be a lot of dust. That's the
Hmm.
main problem.
Yes.
Hmm. So I finished the slide preparation. just 5 minutes before 4 o'clock. Oh, sorry, 3 o'clock.
Actually, yeah, you agreed on a very short notice, so that's actually very, we are very thankful for that actually.
See, problem is now classes are going on, so class,
Yes,
this lab, and so some project for submission deadlines. So I didn't get time for slide preparation. So these
absolutely.
things, it was easier for me because I'm teaching a course on this same subject. So I
Okay.
already had the materials.
Uh-huh.
I'll just take one call.
Yeah, sure, sure.
Okay, so I'm ready.
Yeah, we can start then.
Okay, okay. So let's just continue this. So maybe uh, like I'll not go. I prepared a lot of slide because just 14 slide. I think that end is up to 40 maybe. But anyway, after 5 o'clock, wherever it is, maybe I want to cover the introduction part fully. So let's. I think by 5 o'clock it will be covered. Then I think it's okay.
Okay,
Okay.
fine.
So let's continue. Uh, First, is the pointer? Yeah. Okay. Okay. So this is the picture of 3D topological insulator, and we have the linear band crossing, whereas the carriers it follows zero effective mass. The Dirac fermions are zero effective mass, and then uh, okay, now next what we are going is that as I said that the ingredients which protects the topological insulator, one of the most important part is time reversal symmetry. That is the M term. M term should not be present, so that there is no net moment. Now what happens if you break the time reversal symmetry? So this is the scenario for magnetic topological insulator, where we have the, you can do it by doping, magnetic doping, or you can have the intrinsic magnetic order. So that example is like chromium or vanadium doped bismuth selenide or bismuth BiSbTe3, like that compound. So these are from the experimental reports, by the way. Or you can have, you can introduce the time reversal symmetry breaking by proximity effect. Let's say you have a topological insulator, you make a device so that you deposit one layer of ferromagnet, so that through that deposition, through that interlayer exchange interaction, the ferromagnetic can induce spin polarization effect into the topological insulator. Okay. Or you can have compound, like it's a very rare coincidence, or example is manganese bismuth telluride. Like last few years, I'll say, like there is a boom of research activity in this direction. The reason is very simple. Reason is very simple. I'll explain in the next slide. Manganese bismuth telluride, why it is so exotic. But this is the overall what happens if you break the time reversal symmetry. The consequence is that, as you see that the this in between layer you can make the you can devise, you can design the device. By the way, this is taken from this Nature Material paper. Let's say you have a device where you deposit two different two ferromagnetic layer with different coercive field. So one is easy and another one is hard ferromagnet, so that it is possible that you can independently align these ferromagnets either same direction or opposite direction in like our own way, whatever way we want. So if there is no ferromagnetic these layers, then the in between layer, it was a topological insulator. We had the protected edge state. That is what we had the both the crossings. But if you polarize both the ferromagnetic layers in the same direction, then as a consequence, the one of this layer, because now time reversal symmetry is broken, one of the layer will be crossed, whereas the chiral edge state associate with the up spin only will survive. So you have one edge state, means it is the same picture of quantum anomalous Hall effect. So now the edge state will give the quantized conductance of E square by H. Now, second thing is that if you independently polarize, let's say opposite direction, so one is up spin, another one is down spin. So up spin breaks the down spin polarization, whereas down spin breaks the up spin polarization. Consequence is that both the edge states are gone out from the system, or let's say the gap from the system. That is what is shown from this. See, the top and bottom surface of the topological insulator is already gapped. But with this proximity effect, we are now manipulating the edge states. Either one of the edge state is protected, which is the topological like quantum anomalous Hall effect, or both of the edge states can be gapped. Now, if both of the edge states are gapped, you will think that this is an insulator, but this is not an insulator, because other conditions are automatically satisfied. Like for example, strong SOC, it is still valid. Band inversion still valid. What is the consequence of them? Consequence is that you have the edge state which is gapped out, but the band inversion still intact in the system. Consequence is that it gives rise to a charn insulator kind of. This is where I was saying that I will be covering the charn insulator. This is the charn insulator. Charn insulator means the edge states are also gapped, whereas the bulk is having the band inversion. The topological state is still protected. It's a non-trivial material without edge state. So this is the Chern insulator. This is also called the action insulator. Sorry, axion insulator case, what happens is that it is E dot B. E dot B, it is I'll be covering anyway another one, because E dot B means you understand that when we apply the polarization and the magnetic field, there are two things. One is that because of this axion insulator, if you apply electric field, you can induce the magnetism in the system, or if you apply magnetic field in this insulator, the axion insulator case, you can have polarization of the induced polarization. So that's why it is called electrodynamics, axion electrodynamics, as well as you have the magneto-electric coupling in this case. Okay. So axion insulator and the quantum anomalous Hall effect is both satisfied by manipulating in this magnetic topological insulator. So this is a comparison I have made. So how different states you can observe, like in a normal topological insulator compared to the magnetic topological insulator. Time reversal symmetry is, of course, it is preserved for normal topological insulator, whereas by inducing magnetism, you breaks the time reversal symmetry. Time reversal symmetry. Then the surface state, it is gapless in normal topological insulator, whereas magnetic topological insulator surface states can be gapped out. It can be either one channel or both channel gaps out. It depends on the situation. Hall effect, in this case it is zero, whereas it is in this case quantum anomalous Hall effect you can get. So like that, this is different states. Here I am showing the manganese bismuth telluride. I said that this is one of the rarest example where we observe for example, here, if you want to have a proximity effect, you need to do MB, you need to use the MB and do the deposition. But in MnBi2Te4, this is the bulk compound, you can get the same effect. See, manganese bismuth telluride, you can observe it as a layer. Uh,
Yes, there is some technical issue, I guess. The screen is not being shared.
okay, now is it fine?
Now it's visible. Yes, yes, yes. Now it's visible.
Okay, okay, sorry. How far it was visible?
Yeah, till
Like,
here only it was visible. The magnetic topological insulator.
okay, okay, okay. So then it is fine. So manganese bismuth telluride, as I said, that this is one of the rarest example where you can observe these effects in the same compound. See, if you want to observe this effect, you need to have very sophisticated experiment, like you have to use MBE kind of, where you make the deposition, layer by layer deposition, and you can build the device where you have to control the composition. As you can see, the composition is so complex and controlling is very, very tough. Not everyone can do it. Okay. However, MnBi to Te4, we don't need to do any compositional variation. Nature provides it for us. This is a natural gold single crystal with layer by layer magnetism, as well as, see, in between it is bismuth Bi to Te3. Bi to Te3 is a bismuth telluride. It is the topological insulator. And Mnte, you can think of Mnte, bismuth telluride, again Mnte, again bismuth telluride. So it is like natural grown layered compound. Bismuth telluride in between two magnetic layer of MnTe. So these MnTe layers, because of its exchange interaction, it is antiferromagnetically aligned. That is the ground state magnetic property of this compound. But by external magnetic field, you can polarize these spins in the same direction also. You need little bit high magnetic field. But as a consequence, you can observe that, you can understand that this compound, you can just just the cleave the compound with the natural cleaving, like people what they do with the device fabrication using a 2D material. You can control the layer by layer. If you can, so even there are reports where it is shown that if you make MnBi to T3 with 1378, sorry, 1379, like odd number of layers, you get one property, because one MNT layer will be kicked out. Whereas if you make 2, 4, 6, 8, like even number of layers, your property is different. It is so precisely controllable, the property for this compound. So that is why this is a natural, like nature gifted compound, and lot of investigation are done in last few years, a lot of nature science papers. Now, of course, as I said, real example is MnBa to T4, or you can make a heterostructure, or even chromium dope bismuth Sb telluride compounds. You can have this quantum anomalous Hall effect, but most of them are millikelvin, very low temperature effect. Now, what is the another part I'll go is that what is the consequence when you gap out one age state? Okay, because in the topological insulator, you had the two different age state, one associated with the upspin, another was from the downspin. Now, by artificial means, you are gapping out one age state. What is the consequence of that? Mathematically, for inside the topological material, inside of it, what is going on? So inside the material, when a to age state gaps out, what it gives rise is, it is called the Berry curvature. It introduces Berry curvature hotspot on the compound. So Berry curvature, I will go into detail. I think already in the previous lectures you got already one flavor, but still some detail like discussion without going to the mathematics. I'll try to explain in the simple words. It will be like refreshing up. So, so what this hotspot, the Berry curvature does is that it is actually the equivalent of the magnetic field, but in the momentum space. So, moment you have the magnetic field, what magnetic field does is that it induces a Hall effect, because if there is a charge carrier, you have the magnetic field, it expels those charge carriers towards edge direction, like towards the outer side direction. Same way in the this material, if there is a one channel gapped out, when it induces the hotspot, curvature hotspot, those carriers from that edge on that, let's say, edge state, it will be automatically getting scattered, and it will add up to the other channel, the remaining channel which is present in the compound, because one scattering means it flips the spin also. It is not only that plus k direction will get reflected to minus k with the same spin. If one scattering happens, then plus k goes to minus k, but up spin goes to down spin also. As a consequence, the spin momentum locking and the Berry curvature effect, the edge state is protected in quantum anomalous Hall effect. Now we come to the next compound, next level of challenge, where we are saying that the surface state of this topological insulator, which was the band the crossing, was the Dirac cone. So the quasi-particle excitation of those the charge carriers, it was having Dirac cone, but the bulk was gapped out. Bulk was having topological insulator state, and irrespective of band inversion, it was gapped out. It was an insulator state. Whereas in the Dirac semi-metal case, we have the same quasi-particle excitation of the surface state of topological insulator like a Dirac cone, but now same Dirac cone happens in the bulk, inside the material itself. Now the material is metallic in nature. It is not gapped out material. Okay. So what is the condition you have to satisfy so that you can have such protected band crossing, like linear band crossing, in a in the bulk of the material, because the linear band crossing carries huge importance, as I explained. Like linear band crossing means it is massless particles. Massless particle means the mobility will be huge, MR effect will also be huge. So it has vast potential for application point of view. Okay. So that is why the Dirac semi-metal is another one stage complexity addition to the topological insulator. So what are the things, essential ingredients we need to protect the Dirac semi-metal? One is of course the time reversal symmetry. Time reversal symmetry must be protected, and as I explained previously, the time reversal symmetry gives rise to Kramer's degeneracy and spin momentum locking also. Second, the new addition what we are introducing here is that the crystal symmetry plays a very dominating role. A particular symmetry now must be protected, which is the inversion symmetry. The inversion symmetry induces parity in the system. I will be explaining how inversion symmetry introduces parity and what is the implication of this. There is a very important logarithm also, like Fu-Kane relation and theory are there. So it's very important. So let me just cover one by one what is important. So here is the difference between Dirac semi-metal and topological insulator. So bulk is gap, bulk band gap. Dirac semi-metal case no, because you have the protected band crossing, whereas topological insulator has a finite band gap. Now band touching happens at the Dirac points. There is no band touching in the bulk because bulk is gapped out. Conductivity, bulk conducts, bulk is of course insulating because it's again gapped out. Surface states, it is not essential for Dirac semi-metal surface states. I will be explaining little bit later why it is not essential surface states, but still it is topological, like topological non-trivial material without surface state, without topological invariance. So topological invariant for Dirac semi-metal is not defined. It may be zero, it may not exist, but still it is quantum material. So I'll be explaining why. And topological insulator case, it is always present surface states, and the topological invariance is the Chern number in that case. So time reversal symmetry is essential for topological insulator, but Dirac semi-metal case it's important. It gives rise to Kramer's degeneracy, but Kramer's degeneracy is not enough. Let me put in this way that having Kramer's degeneracy is not enough for having Dirac semi-metal, because you see in the bulk the high symmetric points already has the Kramer's degeneracy, but not all materials are Dirac semi-metal, not all band crossings are protected. You need additional symmetry in the name of parity. Okay, so which is introduced by inversion symmetry. If together is present TRS as well as inversion symmetry, then only that band crossing will be protected, otherwise not. Okay, so the TRS, this I have already discussed, that TRS gives for the spin half particle, the Kramer's degeneracy it introduces. It allows band crossing of the two degenerate bands, and it gives rise to 4 degenerate band crossing. So now next is important part, why inversion symmetry matters and how the symmetry this forbids the bank opening, or let's say how the inversion symmetry protects the band crossing in Dirac semi-metal. So what symmetry, inversion symmetry does is that this is the operator for the inversion symmetry. This is the P operator. It is also called the parity. Under this operator, what happens is that K becomes minus K. Okay. So for the Dirac point, which has the two band crossing without different symmetry, then must have the, see in the Dirac point, earlier we said that it must be in the time reversal invariant point. Now we are saying that at the time reversal invariant point, the bands which are crossing with each other, they must be of different parity. If they are from same parity, then that band crossing, even though it is at time reversal invariant momenta, it is not protected. It will be gapped out. Okay. So what is parity of the band? Parity of the band means if you have a, let's say R, a position, then under this operator parity, it becomes minus R. So obviously the wave function psi becomes minus R, and it can be plus minus psi. Plus minus psi means plus means it's the even parity, minus means it's odd parity. This is very like I think standard quantum mechanics. You have seen that even parity means it's the symmetric wave function, whereas odd parity means it's the odd wave function. Okay, as simple as that. So what is the origin of this parity, or let's say from where this parity comes in a compound? That is also very important to understand. So in a compound, the atomic orbital, because of atomic orbital, this wave function can be written in two parts. One is the radial part R, another part is the angular part. Under this angular part, What is that? The angular part is can be written as minus 1 to the power L into YL under parity operation. Whereas this minus 1 to the power L is the parity term. And who controls that parity? You see, this is the L. L means we have different material, different atoms, where the last electron is sitting. That orbital, each orbital has different L value, and that is the same L which is controlling the parity. As simple as that. So if your orbital is s orbital, then L equal to 0, then parity is obviously even parity. If it is p orbital, then L equal to 1, odd parity. D orbital means even parity. F orbital means it's odd parity. So this is how the parity of a function, or let's say the psi can be defined, or let's say the band can be tagged with. Each of the band in the material can be tagged, like, because you can know what is the origin of that band, who contributes, which element contributes to that band. You can do it from theoretical calculations. If you know which element contributes, then obviously you know what is the L which is playing a role here. If you know the L, then you know the parity of that band. Now, in order to have the Dirac point, you must have two bands crossing with different parity. Now, how to? This is a Fu-Kane method. This is a very popular and very famous. So this is named behind Fu and Kane. They are one of the like two most famous scientists in our time. Okay, so and they have came up a very nice, very simple way of theoretical approach how to find out whether a material we are dealing with is a quantum material, or let's say topologically non-trivial material, or it's a trivial material. How to find out in a simple way? So for that, what you need to find out is that in its the Brillouin zone, you have to go into its Brillouin zone. In that Brillouin zone, you have to calculate this term delta, which is multiplication. This pi means it's a multiplication of this function. What this function represents? This is the parity of that band. Let's say there are, I'll give you an example. Let's say there are four bands. Then each of these four bands parity you have to multiply so that you get this term delta. Once you get the term delta, then you have to calculate this global topological invariant. See, in a Brillouin zone, you have several topological invariant points that I have explained in the previous slides, right? Sorry, many slides back, like gamma, m, r, several time inversion, like time reversal symmetry invariant momenta points. So you have to calculate this delta at each of this time reversal invariant point. You have to see how many bands are crossing at that, what is the parity of this each of these band, make a multiplication, and then for all these delta values, for all these topological invariant, take a full multiplication. This will give rise, let's say, either plus 1 or minus 1. If it is plus 1, that means nu is 0. If it is minus 1, that means nu equal to 1. Nu equal to 0 means it's trivial. That means it's the even number of parities present. So it's a trivial material we are talking about. So this captures the band crossing over the entire Brillouin zone. You no need to do detailed, complex mathematical calculations. Just look at the parity of the bands and find out where these bands are crossing. If it is time reversal invariant point, make it counts. If it is not, it doesn't matter. It's accidental band crossing. Again, if it is accidental band crossing, which it is not covered here, you have to check whether that accidental band crossing is protected by crystal symmetry or not. If it is not, then doesn't matter. The moment you incorporate SOC, that band gaps out. Okay. However, a time reversal symmetry invariant SOC, that crossing is protected. So that is why the parity of those time reversal invariant momenta is important, and we are taking into account. Now, if it is plus 1, then we have even number of parity inversions. Then it is trivial insulator. Or if it is minus 1, then it is odd insulator. See, this gives, one gives it's a topological materials, but whether it's a trivial insulator or topological insulator, that is given by whether it is plus 1 or minus 1. So this is, we can do the follow the steps. So we have to calculate delta, then multiplication of all. then you have to find out whether it is trivial or it is like +1 or -1. If it is +1, then it's a trivial material. If it is -1, then you know there is a odd parity somewhere present. Even though all the like the age states, whatever topological states it annihilates, there will still be one crossing which will be left behind, which will retain the topological nature of the material. That is why the -1, that is the meaning of the -1. So this is the example. Let's say there are four time reversal invariant points are there, and this is the different time reversal invariant gamma, x, l, and m, and each of these point you calculate delta. Okay, like let's say there are 4 or 5 bands has crossed. So what is the net parity of that? It can give either +1 or -1. So this is how you get. Now what you have to calculate this is just to make a multiplication of all these time reversal invariant momenta. If it gives -1, you have topological insulated. Otherwise, it's a trivial material. This is how the calculation is done, or easy way of understanding. Let's put in this way that how to find out a material, uh, topological or non-topological. Next, we are going that we have the Dirac semi-metal. I have already explained the ingredients. Now we are going to the next level of complexity. The two which protects the time, this band crossing, the time reversal symmetry or inversion symmetry. Both of them should be present for Dirac semi-metal. What will happen if you break either of them? Any, not both. Again, I am saying not both. You should not break both. If you break both, then you end up with a insulator. It's a non-trivial material. It's a like, sorry, I am mixing up. It's a non-topological material. So we are discussing a condition where out of the two essential ingredients, one time reversal symmetry, another inversion symmetry, you break one of them. If you break time reversal symmetry, you get magnetic while. If you break inversion symmetry, then you get non-magnetic while. Because if you break inversion symmetry, then time reversal symmetry is protected. Time reversal symmetry is protected means it's a non-magnetic materials. So you can have either condition. You can have while semi-metal. So you can have magnetic while, you can have non-magnetic while. There are two different class. But irrespective of whether it's a magnetic while or non-magnetic while, the behavior is, global behavior is same. What is the global behavior? Once you break either of this symmetry in the Brillouin zone, in the high symmetric points, or wherever you have the band crossing, it is not necessarily at the high symmetric point. You can have it in between two high symmetric point also. You have these points which is called the while points, and it act as a source and sink of the Berry curvature. So what is this Berry curvature? And I'll come to that next. But so these act as a source and sink of the Berry curvature, and on the surface of the material. By the way, this is on the bulk of the material in the momentum space. On the surface of the material, they are connected by this edge state, which is called the topological edge state, Chern, the Fermi arc edge states. Okay, this has a direct connection with the Chern number, whatever we have discussed. It is, let me explain, let me tell you that whatever topological invariant we have explained, meaning does not change. Meaning is the same everywhere. Only thing is that context varies. What kind of topological material you are dealing with, depending on that, the nature or explanation or the source of the topological invariant will change. If it is quantum Hall, then C or Chern number represents the Landau levels. If it is your quantum anomalous Hall, then it's not Landau level. It is the edge states. What here the Chern number represents, the chirality of Chern number, charge, topological invariance, what it represents is that the quanta of the Berry curvature flux coming out from the source or coming in into the sink. I'll explain to details what is that. So what you have to do is that you have to consider an imaginary surface around this Brillouin zone, and you have to theoretically calculate what is the strength of the Berry curvature coming out from that point. It is seen that it is multiplication of a integer, and that integer is the topological invariant, which is the Chern number. Generally, for most of the compounds, like almost 99% while semi-metal case, this is plus minus 1. Plus 1 means it is source of the Berry curvature, sink is sink of the Berry curvature. However, there are exceptional cases, chiral crystals, chiral topological materials, where this Chern number can be 4. And this is the maximal Chern number that nature can provide. You cannot have Chern number more than 4. It is not possible. Okay, so what is the Berry curvature? Berry curvature means it's a basically geometrical phase of matter. And easy way of understanding is that let's consider that you start you like parallel transport case. It is generally explained how to understand the Berry curvature or Berry phase. Let's start from the center on the top, where you have this. Let's consider that you have spin half particle you are dealing with, and because of the magnetic field, the spin is always like it is tangentially from that its k direction, and always in the downside. Okay, the spin direction cannot be changed. Now what we are doing is that adiabatically we are taking this point, go to equator, then we go 90 degree, and we again back to the initial point. If you come back, as you can see, the initial spin and the final spin, even though initial and final states are same, but the spin direction is different. Because of this spin direction, we induces the Ferry phase. This difference is comes the Ferry phase. This is this deflect angle of rotation, this gamma. It actually represents by Ferry phase. It is not proportional, but it is technically represents the gamma. Whereas the Berry curvature term, it represents the solid angle. So Berry curvature, Berry phase is not the same, but they are very, very important. Why? And from my context or whatever quantum material context we will be discussing, Berry curvature is much more important than Berry phase. They are of course interconnected. One can be derived from the other or calculated from other. This is how you can say the Berry phase is in the momentum space or parameter space. So as you can see, these you can connect, you can always define, like in the real space you have the magnetic material like magnetism. In the magnetism, we have the Berry connection, which is the vector potential A. In the same way, in the parameter space or momentum space, you can define the Berry connection. Like gauge potential, here itself is called Berry connection. Whereas there is a B is called the magnetic field strength B is curl of A, the vector potential. Similar way, the omega is the Berry curvature. Berry curvature is curl of this same A, Berry connection. What is phase? Phase is integration of this Berry potential with respect to R. It is connected like this, as well as the Berry phase. Same way, the flux, whatever you get flux is phi. Again, the Berry phase, it can be calculated from this Berry curvature. And same way, if you compare the expressions, you can understand that whatever the role of magnetic material or let's say magnetism in the real space you have, there is something, some parameter defined already associated in the momentum space, and that is the Berry curvature or Berry phase. Whatever you think of. Okay. Why Berry curvature is so important? Because Berry curvature is the one which we actually measure. See, in the real space, we cannot measure, like experimentally, you cannot measure gauge potential or flux. What we measure is the magnetic field strength, B. B is the one which we really measure. Same way, when we go to the momentum space, the equivalent parameter of B is so important. That is the Berry curvature. That is the equivalent of magnetic field in the momentum space. We cannot estimate Berry connection. What we finally do estimation is the Berry curvature. Okay. Now, if you know Berry curvature, rest of the things anyway you can derive. Okay, everything is one-to-one correspondence. So this is the connection of the Berry curvature. And now, if you know the Berry curvature, now I am connecting all the parts which I have defined so far in the talk. Parity, Z2 invariance, Berry curvature, Chern number. Now let's connect with each other. How we can understand the global picture. Berry curvature, what it represents, like the magnetic field in the momentum space, this is the expression. It is, as I explained, that magnetic field in the momentum space, and it controls the the electron dynamics. Like in the real space, you cannot have magnetic monopole. You cannot have identical, like isolated north pole or south pole. You cannot have. If there is a north pole, there must be a south pole. So magnetic field starts, magnetic field ends. You cannot have magnetic monopole in real world. Similar way, once we go to the momentum space, you cannot have isolated source or sink of the Berry curvature. If there is a source of the Berry curvature, there must be a sink of the Berry curvature somewhere in the same Brillouin zone. Same Brillouin zone. It is very important. That is why when wild fermion appears, as I said, wild fermion always appears in pair. Why? Because if one wild fermion acts as a source of the Berry curvature, then there must be another wild point which is acting as the sink of the Berry curvature. So that together, if you integrate the Berry curvature over the entire states, everything over the Brillouin zone, it is zero, net zero. Okay. Same concept, one-to-one correspondence of the magnetic field in the momentum space. Only difference is that magnetic field is in the real space, this is in the momentum space. Now, Chern number. What is the connection of the Chern number with respect to this Berry curvature? Chern number means you have to integrate. Let's say that if you integrate the Berry curvature for all the occupied states up to the Fermi energy, then what it gives is the Chern number. And this is the same topological invariant we have repeatedly mentioned. Like you imagine a arbitrary surface around this topological point, or let's say wild point. What is the net quanta coming out? That is the strength of this point, wild point. That is the topological invariant of that wild point. Okay. Next is quantum Hall effect. Quantum Hall effect case, the Hall conductivity, how it is connected with the Berry curvature. It is simply E square by H into C. Into C means already C is connected with the Berry curvature. So Berry curvature is directly connected with your quantum Hall effect. So this is the connection. So if you know the Berry curvature, you can know everything in this quantum material, as you understand. Okay. So this connection was made by David Thouless, and so theory. Now, without mentioning this, it is not complete Berry curvature, which is Pancharatnam phase. And nowadays, it is called Pancharatnam Berry phase. So, Professor S. Pancharatnam, he was PhD student of our C.V. Raman, our Nobel scientist C.V. Raman. And he discovered this phase is that, but this phase is connected, Pancharatnam phase, let me tell that this is connected with the polarization geometry in classical optics. Okay. However, the Berry phase, when Berry introduced, they independently, as per documented, or let's say literature in this way, I don't want to enter into debate. So I'm saying middle path, that they independently, let's hope that they independently derived the expressions or the conclusions they derived. So in Berry phase, it is much more general, whereas Pancharatnam phase, it is in the context of classical optics only. However, both represents the same thing. Okay. And but what I found in the in literature is that Berry phase is more general approach. So maybe that is why people are so Berry phase not introducing Pancharatnam, but it's basically the same thing. Okay. So now I'll be going into the real part. How much time we have? Or should I go at all? Because let me finish in this. Like the future prospect is huge, as you know, from so many lectures and so many topics. That future prospect of quantum material is enormous. Lot of prospects and future. So it is just started maybe 10-15 years back. So it is new field. Lot of things to be explored, controllability and real practical applications. Many things to be done. So so it's one of the hot topic. And yeah, so
Maybe
yeah, actually I
maybe
was
you
going
can,
into
yeah, maybe you can talk for another 10-12 minutes.
okay, okay, fine. So I'll just briefly introduce some exotic things and very specific, not the general introduction. And
Yes.
yeah, in 10 minutes I'll just stop. Okay, so as I said that while semi-metal can be of two types, as you can see, either time reversal symmetry broken, that means it's a magnetic while, or inversion symmetry broken, that means it's a non-magnetic while. Okay, so time reversal symmetry broken case, it was discovered. So this is 2019, and it is the same time. Let me tell this. All these three papers, it appeared from the page numbers, as you can see, same day in Science, all the three, and from Claudia's group where I did postdoc, and I'm the co-equal contribution second author in this page. This is paper. This is my sample and experiment. So this is another sample where this work was done in Enke Liu's sample in Claudia's group. But all these three papers came on the same day in Science, were discovering the magnetic while for the first time, and this is the consequence of the magnetic while. So if you have a magnetic while, then obviously you have strong Berry curvature, and integration of the Berry curvature, as I have shown, it gives anomalous Hall. So if you have integration of the Berry curvature and anomalous Hall and while point, this is very important, that while point has to be very close to Fermi energy. Otherwise, this even though there is Berry curvature, etc., far away from Fermi energy, it will not affect the anomalous Hall. Okay. So in these two compounds, it so happened that while points are very close to Fermi energy. As a consequence, you get a large anomalous Hall. But cobalt 2 manganese gallium. So this work is so important because it's a room temperature ferromagnet. So its transition temperature is around 700 Kelvin. The second one is cobalt 3 tin 2 sulfur 2. Here also the transition is high. Anomalous Hall is also high. But here important is that anomalous Hall angle is very high, 20%. It's huge, 20%. Whereas anomalous Hall angle in this case, it is just 13%, as you can see. Okay. So this is the discovery of magnetic while. And if you have anomalous Hall, then obviously if you do anomalous Hall is in electrical transport, you can do thermal transport also. Thermal transport means you can create temperature gradient. I think Shubhajit already gave a detailed talk on this, what it represents. So if you have a compound with wild semi-metal, whereas the Fermi energy is very close to the Fermi, like the band crossing is very close to Fermi energy, like in this case cobalt to manganese gallium. So in this sample, we have observed that this Nernst coefficient, Nernst thermal power is very high. This is in the log scale. So it is few times than any compound ever reported in literature. So, so you can get such exotic properties. Now, second is the time reversal invariant case, like it is non-magnetic while. So one case example is tantalum arsenide, niobium phosphide, niobium arsenide, like this series of compounds. It was discovered 2015, 16, around that. Next is very, very important, which I want to spend 5 minutes. This is chiral topology. As I said that I am co-discoverer of this chiral topology. So why it is so exotic, why it is so important, let me explain little bit. So in the conventional while, whether you take magnetic while or time reversal invariant, or let's say non-magnetic while, like as I say, 99% of the material, always you have a mirror symmetry. Okay, because of this mirror symmetry, these while points appear at the same energy in the dispersion, Ek. So if you want to have a physical property coming out from the Berry curvature, and you want to arrest, let's say, the response of one while compared to other while, I have that is called the CPG, circular photogalvanic effect. Okay, there is one effect I will not have time to cover. So like optical response, you put circularly polarized light in a material, and the response, or let's say the DC current it generates, it is proportional to Chern number of your while point. So if you have two while points active, because you see, depending on the energy, if you this while point is active, then this while point is also active because it's the same energy, right? So if there is a DC current from plus C, then there will be opposite DC current from minus C. So, so if you take a conventional material and do such experiment like circular polarized light experiment, you will not get any DC current, because net DC current, because whatever plus DC current coming out from one while, it will simply nullify from the other. So it is important that you, if you can shift one while with respect to other, then you can probably lock one while point compared to other. You can independently see or map the response of one while point with respect to other. So here comes the chiral, because chiral means structural chirality. Instead of mirror symmetry, you have the glide operation, reflection plus translation. As a consequence, you see, this is the chiral topology. If you look into literature, or let's say in nature, this is very important. Why 2 3 years back this Nobel Prize is given for chiral synthesis? Why it is so? Because today also we do not know what is the origin of life. Our left hand, right hand, these two objects are chiral object. If you look into the living organism, let's say molecules like DNA, RNA, sugar, nature, if one DNA, RNA or sugar molecule is natural grown, it is always right handed. You will never find a left handed DNA. Whereas if it is amino acid, protein, it is always left handed. You will never find a right handed amino acid. In our drug industry, around 56% of the molecule are chiral molecule, and it is proven, experimentally proven, that if left handed chiral molecule in the drug is life saving, same molecules right handed is poisonous. Many people have died because of this. Now why? Because energetically both left handed as well as right handed are same energy. You cannot, the chemical synthesis nowadays we can, like in using some enzyme etc, you can segregate, you can boost synthesis of one chirality with respect to other. But it is unresolved fact how nature builds a living organism, and it 100% it always, like DNA, RNA, it is left hand, right handed, amino acid is left handed. We have no answer to that. So this is quest for the origin of life, and we are trying to understand some part of this with respect to the chiral molecule, because now in the momentum space we have the option that we can control these topological states with the structural chirality of this molecule. Because everything, as I said, the symmetry is the most important part here. If you manipulate the crystal symmetry, the topological states are also automatically changed. So if you, we have shown in any papers, in my papers, that if you go from right-handed chiral molecule while points go to left-handed chiral, your topological states simply change. And this is experimentally observed. So should I continue or stop?
Maybe continue for another minute because this topic is very interesting.
Okay, so I'll just flash maybe because okay, so this work is started back in 2016 when it came this theoretical paper which shows that more than one band crossing is allowed in nature, because in the nature, in the natural wild points it's always two band crossing. However, more than two, whether it is allowed or not, that came first paper is 2016, this paper we said that it is allowed. Okay, then in 2017, this theoretical paper came, these two masterpieces of work from where I started my experimental work and all this chiral topology experiment started. By the way, in the entire world, until like I came from Claudia's group 5 years back, until at least 2 3 years back, whatever discovery was done, topological chiral crystals, there were I think 4 or 5 crystal growers whose crystal was used for all these investigations. Like you go to any RPS beamline in entire world, somewhere you will find my crystals are there. Because the crystals, it's because controlling the structural chirality and growing mono chiral crystal is not easy job. The anyway, it's fine. That is a next whole, how to control is a different class. But what this theoretical paper said 2017 is that am I audible?
Yes, sir. Now you are audible.
Now you're audible,
Okay.
sir.
Intermittently, there was some break.
Okay. Okay, so what this 2017 paper, what it says is that in the high symmetric points like gamma point and R points, you can have this multifold band crossing which are protected by the Kramer's degeneracy. So these are Kramer's wild point. Why the Kramer's wild point? Because time reversal symmetry is protected. These are the time reversal invariant momenta points, gamma and R. As a consequence, the compound which is predicted, this is a series of compound, rhodium silicide, cobalt silicide, platinum, gallium, all are, as you can see, they are diamagnetic materials, like non-magnetic category compound. And in the gamma point, it is seen that there is four-fold degenerate, whereas at R point, you have six-fold degenerate band crossing. However, the most important part here is that the chart number, which I was discussing so far from the beginning slide, the chart number topological invariant, that is plus minus 4, 4 times larger than any other topological materials. The quantum edge states, or let's say, I'm not considering the quantum Hall effect because that is the number of Landau levels. It's different case. So if you consider the Weil or Dirac topological insulator, quantum anomalous Hall effect, anything you take, this char number plus minus 4 is the maximal char number that nature can provide in any Weil point in nature. So theory, so that is the mathematical calculation prediction we had, and our theoretical calculation also showed that most likely in these compounds, because without experimental verification there is no way this theory is valid. So this is the growth part. So I have grown these crystals using most, these are the flux grown crystals, and some are in CVT, and rest are in the Bridgman growth. I think Professor Surjit Singh already covered this part, so I'm not going into detail. So this is our experimental verification. So we have done the RPS measurements, and from the at the gamma point, as you can see, this is the four-fold degenerate band crossing. At the R point, we have the six-fold degenerate band crossing. Now, if these band crossings are Y points, then what is the experimental proof? So what you have to do is that you have to do energy dependent surface state, and if you can find a surface state connecting from the gamma point to the R point, then we know that this surface state is the Fermi arc. So this is our surface state experiment where we can see that this is the Fermi arc expanding the entire Brillouin zone. It is starting from the gamma and it goes all the way to the, because this is the cubic compound, a cubic compound. So the Brillouin zone is also cubic in nature. So zone center to zone edge on the surface, it is connected with respect to the Fermi arc. Now, this Fermi arc, if you want to have char number plus minus 4, the Fermi arc also would be 4 number. So you must have splitting of this Fermi arc. However, this platinum aluminum case or cobalt silicide, rubidium silicide, these compounds we could not resolve whether char number is plus 4 or minus 4. What we observe is that there is a Fermi arc connecting from gamma point to R point, and this is the surface state. So it matches without SOC, whatever we had, that is the part it matches. So that means char number is present. This is the wild point, but whether it is 4 or 2, we do not know. For that, what we had to go next, okay, char number 4, I'll come. Next is that, can we control these topological states? How these topological states can be manipulated, okay, which is in the momentum space. So what we do is that I have grown the crystals. One is left-handed chiral crystal, another one is right-handed chiral crystals. So the crystal growth parts is explained in these papers. What we see is that the X-ray also from X-ray and EDX also, not EDX, EBSD experiment, not EDX. EBSD experiments also, we confirm the chirality of this. One is left-handed chirality, other one is right-handed chirality, same composition crystals. When we do the RPS measurements, what we find is that, again, let me put in this way one important explanation. What is the Fermi arc? As I said, that if it is the char number is 2, what is the connection of this char number of a Y point, which is the quanta of the flux, with respect to the char number of a quantum anomalous Hall effect? Quantum anomalous Hall effect char number represents the age states. What is the connection of that age with this? Age state here, this is the picture which we have drawn to show the connection. If we have chart number 2, that means 2 age state, this 2 number of Fermi arc, you can think like it is a vertical imaginary cross section of this quantum anomalous Hall. So two number of edge states starting from gamma to R point. And since it is only the edge state, you are observing the surface state, which is the Fermi arc. Two number Fermi arc, two edge state, chart number 2. Here is the connection of quantum anomalous Hall effect with the chart number of wild semi-metal. Okay. Now the experiment. So first we had to prove this is palladium gallium, that this has fourfold and sixfold degenerate band crossing at the gamma point and R point. And with the R phase spectrum, we have proved yes, we have the fourfold and sixfold band crossing, as well as we have the Fermi arc. As you can see, we have the Fermi arc. Now, if you go from left-handed chiral to right-handed chiral, if you see, this is simply mirror image with each other. If one is left-handed, Fermi velocity is like this. Then if when we go from left-handed to right-handed, the Fermi velocity is simply opposite with each other. That means by controlling the structural chirality in term, we are controlling the topological states which is in the momentum space. This is the direct experimental proof of that. Okay. Next, counting of the chart number, whether chart number is 2 or 4. For that, what you have to do is that this Fermi arc, whether it is 1, 2 or 4, we have to do. So for that, what we do is that we deep energy dependent cut. Okay. And we can clearly see that you see the splitting. So 1, 2, 3, 4. 4 number Fermi arcs. 4 number Fermi arcs, 4 number of chart number 4. So this is what we have proved in this paper, as well as in the science paper also we have shown the splitting. So this is how we prove that yes, we have chart number 4 experimentally proved, and we have the chiral topological materials where we have the Fermi arc, and you can control those Fermi arc with applying magnetic field. Sorry, with structural chirality. Okay, should we continue or stop?
The
Uh,
participants and we also are mesmerized with your results, and we are here. Continue. But you are the best judge where you want to stop. Okay, we can take some time.
I'll
But
just maybe two slides, just 2 slides, and then I'll stop. Okay.
yeah,
So
okay.
just give you theoretical background and then we'll stop. So because see whatever we are discussing the quantum materials. First of all, you have to understand that the experimentally what all the consequence we get in the practical application. If we cannot get something in the practical, then what's the point of investigating so much? Okay. So one of the important aspect of practical application was this CPG, which the theoretical prediction was done in 2017, where this prediction says that if you apply a circularly polarized light on a wild semi-metal compound, then you can pump the electrons from the valence band to the conduction band. As a consequence, you get a current, DC current from the material. Just apply a circularly polarized light, you get a DC current. You imagine what will be the application. Like it will can be act as a quantum magnet, it can be act as a switch, it can be act as a detector, everything. Like you just put the light, you have a DC current, quantized DC current, because thus you see what is the DC current? E cube by h square into c. There is no material specific parameter, universal constant into Chern number. That means the DC current is quantized DC current. You apply a circularly polarized light, you get a DC current, and that is a fixed DC current. So this is very interesting if you can do the measurement. That is the problem, because most of the wild semi metal, as I said, whatever it is, always there is a mirror symmetry. As a consequence, both the wild points appear at the same energy. See, for example, niobium phosphide, you have so many wild points throughout the Brillouin zone, but no use of that, because the moment you apply circularly polarized light, the current from one wild point, it will simply nullify the current from the other. Net result, zero DC current. Even though it is there locally, you will not get any current from that. So what is the next level? We break the mirror symmetry, we go to the glide operation. Instead of reflection, reflection plus translation. So we break the inversion symmetry, we break the mirror symmetry. This is the importance of the chiral crystals. So chiral topological materials with 2p to 1 by 3. 2 1 means we have the glide operation. Okay, as a consequence, as you see that these wild points appear at different energy. So this is the EK diagram. As you can see, if you have Fermi energy, let's say in between, then it is very easy that this wild point will be Pauli blocked with respect to this wild point, because let's say you apply incident light, so that what light will do is that it will excite the 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 electrons from, let's say, from the valence band to the conduction band, right? Now what happens here is that it doesn't matter in for this respect to wild point, whatever is the valence band, whatever is the any energy, whatever is the incident energy, always you will find a conduction band available, so that the excitation of the electrons with respect to the from the valence band to conduction band is allowed for this wild point. However, when you come to this wild point, let's consider that this much energy, the conduction band is already filled. So if you incident this much energy, this delta, like below Fermi energy till this energy, this difference energy. So if you apply that much incident energy, then whatever electron will excite from valence band to conduction band, where it will go? It cannot go, because its conduction band is already filled. If conduction band is already filled, then this excitation is called Pauli blocked. So until this much energy difference, whatever excitation of electrons will happen from conduction, from valence band to conduction band, it will happen only in this wild point. This wild point will be Pauli blocked. It is excitation is simply not allowed. Therefore, for the incident energy of this much, you can get DC current out of only one wild point, because other point is already blocked. So this is the potential of these chiral topological crystals. If you can like lock the Fermi energy at a particular suitable point, because if see Fermi energy, if it shifts up or down, you can change the energy, incident energy, until how much energy this will be quantized response you should expect. Now we take rhodium silicide compound. Rhodium silicide, as you can see, this is the gamma point and this is the R point. Therefore, until this much energy, incident energy value, whatever valence band to conduction band excitation will be happen, this is not allowed, because conduction band until this much energy it is already filled. So until this much incident energy, whatever quantized, whatever DC current you will observe, it is basically unfiltered DC current from the gamma point. That is what we expected. But when we do the result, what we observe is that there is a little bit frequency dependence. And then when you cross this energy, what happens is that the linearly more and more electron will start excitation. So the DC current will nullify and it will fall. So trend we observe, but we do not observe the quantized value, the flat value, whatever we expected. The reason is that there is a flat band. This flat band also gives excitation, first thing. Second thing is that this excitation energy, this matches with this trivial band gap. This value and this value is almost same. So when we submitted this paper in Science, almost like two referee accepted. One referee, they said, no, 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 we don't believe your data. Because you don't see as the quantized response. So finally it went to Science Advances. But this is the only experiment available till date where someone has shows response of DC response of chiral like circularly polarized light. So this is, I think we should end here, but yeah. So this is there are many theoretical calculation where it is shown that okay, the Fermi energy can be tuned. How it can be tuned? We can dope rhodium silicide with nickel, and we can shift the Fermi energy. In fact, in my nickel doped also, we have shift the Fermi energy from this point to above. So like that. So I think. Oh, it's already over. Oh, thanks. Okay, thank you.
Thank you,
So
sir, for
any
the thank you so much for the beautiful talk. All of us were really into it. The last part specifically, it was very, very
no, as I said, na, that
correlative one.
Oh, well, I don't know. So,
So if the participants have any question, you can please put it in the chat box. In the meantime, I'd like
yeah,
to ask. Oh yeah, okay. So there is a question from the participant.
what is that? Uh,
Optical excitation can be done by elliptical and plane polarized radiation apart from circular one.
it can be done, na? That is how the see elliptical and plane polarized. Finally, you have to like use two different sources, and you have to create the simultaneously whether it is circularly polarized or not. That is how the experiment was done. Please check the experimental part of this paper. Sorry. Of our the science advance paper. So we have explained the experiment setup also. So in fact, one more paper I can tell you either in this PNS paper or this nature.com. Here also some experiment are done on cobalt silicide. You can check the experiment protocol how this linear polarized like circularly polarized light is generated.
So,
Sir,
in continuation with this, I would like to ask whether this circular dichroism that we normally use for, say, proteins or amino acids for studying the chirality of those molecules, can that also be used for these crystals?
So that I cannot say because this see this experiment it is not of my expertise na? So I
Okay.
understand the physics, then I just contacted this I can tell you the name, that is Orienstein, the final the last author, because I am not optics guy. I do not know anything about the optics. So I just understand the physics part. I have the crystals, so I know what my crystals can give. So I just contacted the groups who has the facility. I just tell them, okay, I have the crystal. This is the physics what I want to investigate. Are you interested? If not, I have other groups also. Because I have the samples and yeah, so they agreed, they did. Actually, this is how these other papers came out because they were taking lot of time. So I went to their competitors. I said, "Oh, these guys are taking lot of time. Why don't you do measurements?" And I told in between that, okay, those guys are doing experiments. So hurry up, otherwise you will be loser.
This is what we got to them also.
See, instead of one paper, we got multiple papers.
And regarding that DC current generated when you eliminate with the circular polarized light, so how typically can you measure that current?
How typically means
I mean, how do you measure that current?
oh, that also the experiment setup you have to look. I didn't
Okay.
put in this. Can you please go through this paper? Then the
Sure,
details
sure, sure.
it is
Sure,
mentioned.
possibly. I'll go right
Because this
through
is
it.
very, very like I'll say like interesting and involved like in physics. Like just imagine like circularly polarized light we are putting in a sample and you are getting quantized response. Like last few years we have been like searching for this compound. I think almost like see, this paper came in 2017, as you see, 2017.
Hmm.
And our paper came when? It came in
20.
2020, right? 3 years, it was a lucky coincidence that I came across that paper. And without this series compound, there is no other paper, no other compound, because no one can satisfy these conditions. You have to satisfy the shifting of this while, right? Higher and
Mhm.
higher shifting, better chance of getting that like you can like higher the energy range you get of the blocking part, because you see when you do the experiment you need little bit decent energy, right? Otherwise
Yes.
it will be in the background. So higher and higher separation, you higher and higher chance of getting current. And also this current is proportional to c means Chern number. In nature 99% of compound c is 1. It so happened that chiral crystal C is 4. Otherwise, you do not have any chance.
Mhm.
That is the like roadblock so far. We have been doping the compounds, manipulating the Fermi energy so that this like energy window we can increase little bit. But yeah, it's very challenging. And after I moved back to like IIT Delhi, almost I'm out of touch. So I go once in a year to Claudius Group in Dresden. I like work 1.5 months, grow the crystals, put the batches, and then I contact from IIT to different collaborator. "Oh, I have this crystal. I want to do this experiment. Will you do?"
Yes. That's
So
we
that is,
always
but
need to do. Yeah.
otherwise, yeah, I'm out of touch technically because yeah, in because now I have my own group and my focus moved from chiral topology to magnetic and
Magnetic.
transport measurements more. Let's
Hmm.
put in this way
Okay.
because I don't have facility. Now that's the another roadblock. I
Absolutely.
don't have characterization facilities, so otherwise students will suffer a lot. So I had to pick the research problems in such a way that we can do the characterizations here with our
Yes.
facilities. So anyway, let's see.
Yes, sure. And there are a couple of questions from the participants as well in the chat box.
Ah, uh, what is chat? Okay. Give rise to exotic quantum such as quantum. Okay. Okay, let me go to that slide. Where is the slide? Yes. Please look at this plot, this right hand side. Okay. You have topological insulator. When you have topological insulator without any magnetic doping, without any proximity effect, you get the edge states. But if you apply the magnetic field and align these ferromagnetic layers in one direction, then what happens is that you induce a proximity effect, right? Because of the exchange coupling, exchange interaction you induce. So the up spin only will protect, but the down spin, it will be gapped out because now down spin with respect to the up spin of this ferromagnet, it will simply annihilate, right? It will be gapped out. The moment it gaps out, it is what it does is that it induces Berry curvature hotspot. Because of that Berry curvature hotspot, the electrons which was there in that channel, it adds up in the existing channel because of the momentum locking, spin momentum locking. As I have explained here, please TRS, please go through the, you will have the video lecture anyway, so video recording. So the TRS, how the TRS protects the scattering, because one is gaps out means it is now like subjected to scattering. Scattering in presence of the Berry curvature. So scattering in presence of Berry curvature means it's like a Hall effect. Hall effect means apply magnetic field and you have the carriers. Carriers will have the Lorentz force. It will go to the edge. Same way the Berry curvature will be internal magnetic field. It will like let's say repel the spins towards the edge state. Since it is one direction, let's say plus k direction getting scattered, then it will go to minus k. Minus k means down spin. So if it was up spin gaps out, then it will become down spin. So down spin already it is protected, so it will add up in the down spin. Or if you manipulate the ferromagnet so that the up spin is protected and down spin gaps out, then all the spins in the down spin, it will be add up. It will add up contribution in the up spin. That is how it is in, it induces the edge state, or it protects the edge state. Let's put in this way. Anything else?
No, so all the Berry curvature one is done.
Okay.
Hello, sir. Hello, hello, hello. I
Dr.
really, it was nice talk. I was not questions actually. I just want to hear your view on the quantum things going on in India. You know, this quantum mission is going on, and there is a big halla. What do you think that how we can contribute, or where are we actually? in this process. Because although this course is quantum materials, but I think I mentioned that this is also somehow in support of quantum mission. We are organizing this quantum series from QT-01 to QT-011, including quantum computing, quantum communication, sensing, materials, all these sub areas.
Uh,
So, yeah.
uh, See, first of all, I'm just a junior faculty, as you understand. Like anything negative I say, it will be add up. See, my project didn't go through in quantum mission. As far I can see that the projects which is passed, it is the talk which I gave today, the quantum material. I don't see any project which is funded where the quantum material is involved.
Exactly.
whatever I I discussed today in the talk, quantum materials. That's why I think you caught the point I said, right? The real quantum material I discussed in between, right?
Mm,
That in India people are doing few decades, right? The magnetism, real space effect, etc. It is frankly speaking, it's not the quantum material that hype is going on, or the tab, or which outside India people are so excited because it came just 10 years back.
yeah,
So it is different than the quantum materials that is being focused, as I can see, because see, I didn't see any project which is funded on Dirac, Weil, or related topological states. I didn't see any project. It is just it should be named as quantum photon mission, actually quantum photonics mission, not quantum mission, material mission, in my understanding.
okay, okay,
Because
okay. I think you got it correctly.
see,
So
I, I
basically,
don't know, this is what
yeah.
it is.
So the next thing was let us see that you have really nice crystals, and supposedly I was also there in CPFS for some time from
Okay,
2007
okay.
to 10, 11, and yeah, I do high pressure in all these type of materials. So we study materials under high pressure. So I saw
Okay.
very little results maybe on your crystals under pressure. Or maybe you have not included in the presentation.
Actually, a
So,
lot of things are there. I just focus something which
mm.
I can cover in these times.
But these materials are really interesting under high
Uh,
pressure also because the symmetry breaking we can control, we can tune these
uh,
structure under moderate pressures, and then we can play around.
hmm.
Yeah. Okay, sir. Thank you so
Okay,
much for being with us,
thanks.
accepting the
Thank you
invitation
for.
at very short notice. Yeah, it was
No, no,
really
it's fine.
nice. Yeah.
It is fine. Thanks for inviting also and giving opportunity to speak. So it is nice.
Yeah. I would like to extend our invitation that do visit us sometime in Jaipur,
Sure, sure, sure,
very far from
sure,
Delhi. Okay, sir.
sure.
Okay, sir. Bye.
Don't tell me, sir, sir. Don't tell me I'm much junior than you. Like
But, but
I'm junior
you
faculty.
you
Don't
are
tell
the
me.
expert. Okay, 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 fine. So, yeah.
Okay.
Okay, bye.
Okay. Thank you. Thanks. Thanks. Bye.
Thank you so much.
Thanks. Thank you. Thanks.